Episode 99, Black Holes and Big News. Hey everyone, Chris here, doing a little solo episode, just a very brief episode here for number 99, for reasons that'll become apparent in a minute. And those of you who are so far in advance of what I'm talking about, you already know why. But anyway, we'll come to that in a second. Two big pieces of news for this episode. The first is that just in the last couple of days, astronomers from the Event Horizon Telescope, the EHT, have put out the most amazing image. It's an image of the supermassive black hole at the center of the Milky Way galaxy. Now, that may sound a little bit like deja vu to some of you. Haven't we already done this? Well, going back a little way, all the way back to episode 35 back in 2019, didn't we talk about the first image of a supermassive black hole? Well, yes, we did, but it wasn't our supermassive black hole. That was an image of the really supermassive black hole at the middle of M87, Messier 87, which is a galaxy which is about 55 million light years away, and there's a super honkin' black hole at the middle of that, which astronomers managed to actually take an image of, if you remember. And what did it look like? It looked like a big fuzzy donut, right? And the black part at the middle of the donut, that's sort of the shadow of the event horizon of the black hole itself. And then the big fuzzy glowy bit around the outside, that's the glowing gases that are swirling around this thing as they're bent by the extraordinary gravity of the supermassive black hole. So we've been through this, right? Well, yeah, that was the first one that anyone had ever managed to actually take an image of. This is different, though. This is the one that, when that announcement first came out of the M87 star supermassive black hole back in 2019, everyone thought maybe they're also about to release an image of the supermassive black hole at the center of our galaxy, the center of the Milky Way, what's known as Sagittarius A star. That's not A star as in a star. It's A star as in A asterisk type thing. It's called Sag A star is what they call it. And it's the supermassive black hole at the center of our Milky Way galaxy, which we were pretty sure was there because we can see stars whipping around and things like that, pulled around by some huge mass right down there in the heart of the galaxy. But we just never been able to see it because it's a black hole, right? And using the same techniques that they used back in 2019, actually the same kind of observing run, an image has now come out of the Sag A star black hole at the center of our galaxy. So it does beg a few questions. Why did it take so long? Why was M87 star relatively easy to do and ours, which presumably is much closer, so much harder? Well, let's go into it a little bit. First of all, like how did they do this? So the Event Horizon Telescope is actually, it's not one telescope. It's a bunch of telescopes that are all connected and correlated together using what's called very long baseline interferometry. It's just effectively combining the signals from telescopes from all over the world to create a telescope, one unified telescope system, which effectively has an aperture the size of the planet. Because you need that in order to see something which is so small, so far away. So these were telescopes which are spread out from Mexico to Spain, Hawaii, right down to the South Pole, giving one huge dispersed collecting area. It's really quite a staggering thing. You couldn't really make a telescope aperture bigger than this unless you actually start going and connecting things together in space. The reason they had to do that was because what they're looking at is actually really, really small, right? Even though we talk about supermassive black holes, and you think these things must be enormous, and they are pretty big, they're still really small in comparison to the rest of the galaxy, right? So let's take a few stats here. The supermassive black hole at the center of our galaxy, right, Sag A star, is 27,000 light years away. Right? We've got to look through all of the rest of the galaxy down towards the center to actually get to where it is. 27,000 light years away. It's around 4 million solar masses. So that's a lot. That's 4 million suns, but squeezed into a space which is only about 30 times wider than the sun is itself. So that whole fuzzy donut on that image that you've probably seen, and if not, take a look at your podcast player, because the chapter art will be showing it. That whole donut will fit inside Mercury's orbit around the sun, right? So we're looking at that only from 27,000 light years away. To put that in some other perspective for you, right? Some people, some wags on Twitter have been asking, well, why is this image so fuzzy, right? It's not that far away. It's fuzzy because this thing is so small that if we were to point the Hubble Space Telescope at it, Hubble's most accurate, its most precise camera, 1 pixel on that camera is way, way, way larger than the donut that we're looking at. So this supermassive black hole is so tiny, you wouldn't even notice it as a tiny blip within the Hubble Space Telescope image. Just couldn't do it. So that's why we need this ridiculous EHT telescope, the Event Horizon Telescope, with its very long baseline interferometry, just to get a chance to see this thing. But the other reason it's taken several years beyond that first image back in 2019 of M87 star to see Sag A star, to get an image of it, is because it's much harder to get an image of. Well, why is that? I mean, it's much closer. It should be easier, right? Well, part of the problem is that it's much smaller than M87 star, right? Some stats on M87 star. It's much further away. It's like 1,000 times further away, 55 million light years away, complete whole other galaxy. But it's also like more than 1,000 times more massive than Sag A star. The supermassive black hole at the center of M87 is really big. It's like 6.5 billion solar masses. And its donut, right, the bright donut ring of the image that we were able to see back in 2019, that takes up a bit of space, which goes well beyond even the size of the orbit of Pluto in our solar system. So it's about roughly 1,000 times more massive than Sagittarius A star in our galaxy, but it's also much, much further away. So actually in the night sky, it ends up being approximately the same size in terms of sort of angular size. So why is Sagittarius A star harder to see then? Haven't I just made the argument that they should be about the same? Well, okay, a couple more reasons. One, in order to see the supermassive black hole at the center of our galaxy, we had to look right through our galaxy. And there's a lot of stuff in the way, particularly as you get down towards the center of the galaxy. There's a lot of gas and dust and other stuff, stars, getting in the way. And you've got to look through all of that, which is really hard. But the other reason is that because Sag A star is 1,000 times smaller than M87 star, what that means from a physics point of view is that anything that's happening to that smaller supermassive black hole is happening 1,000 times faster. Because it's 1,000 times smaller, things can influence it 1,000 times faster. And so all of the swirling gas and stuff that's being ripped around it at incredibly high energies and high speeds, that's all changing 1,000 times faster than it is for M87 star that we looked at back in 2019. And so it changes, it fluctuates so much faster that getting a lock on it, trying to get an image that looks anything other than just a blurred out mess, is really, really hard. And it's taken several more years of image processing and data collecting and data refinement to get the image that we see today. And in the end, they actually look really quite similar. It's quite staggering that the two images of two completely different supermassive black holes in two completely different galaxies doing completely different things actually end up looking really, really similar. And they both reflect our best knowledge of Einstein's general theory of relativity. They agree with Einstein's results really, really well. So big thumbs up for both astronomy and physics there. So that's the first thing that I want to tell you about, is the fact that we've seen this thing now. We've known for a really long time that the supermassive black hole at the center of the Milky Way galaxy was there, but now we've seen it. And it's a little bit more special than the first one we saw back in 2019. It's special because because this one's personal. This one's ours. And speaking of personal, the other thing that I wanted to tell you about, the other piece of news is that after lots of waiting and after lots of wondering when it was going to happen, I'm very happy to report that my co-host here on Syzygy, Dr. Emily Brunsden, has finally given birth to a small human child by the name of Robin. Welcome, Robin, into the world. It's really great to have the newest member of the Syzygy fan club out here on the outside. I even got to have a little bit of a cuddle earlier today, so I can report that things are going well. So I just wanted to let everyone know that. Emily's doing well, and she'll be back with me on the Syzygy podcast as soon as we're able to make that happen. Those of you who have had kids know, hey look, all bets are off at that point. But we will be back. We're just not entirely sure when. So we'll see you soon.